Okay. Hello, I'm Phyllis Stabeno. I'm in lead of the EcoFoci program at the Pacific Marine Environmental Lab in Seattle. I had hoped to be there today, but life happens, and so I'm doing it remotely. So anyway, so good morning or afternoon as the case may be. I would like to talk today or present some information today on the changing ecosystems in the northern Bering Sea and the Chukchi Sea. These data have been collected by a wide range of collaborators. It's an extensive area, and observations have always been limited in the region. EcoFoci is a long-standing cross-line office partnership between the Alaska Fisheries Science Center and PMEL. We also partner extensively with other federal and non-federal groups. The mission is to expand the understanding of the marine ecosystem in the North Pacific, the Bering Sea, and the US Arctic, and to apply this expanded understanding to management of the living marine resources. So where do we work? We work primarily in the Alaskan waters. You can see here kind of where we've collected data. This is a 35-year program, so there's a lot of data that's been collected. Historically, FOCI has 6 cruises a year in this region, over 100 days at sea. 3 are led by fisheries and 3 are led by PMEL. So the dots here are CTDs, bongos, that type of thing, shipboard measurements. In addition, we maintain long-term moorings. There are the red dots there. There's 4 in the Bering Sea, and there's another 4 in the Arctic. On the southern Bering Sea shelf, we will deploy next year a mooring for the 28th consecutive year that measures biophysical things, measurements. It does all the physics, zooplankton, phytoplankton, nutrients, CO2, and passive acoustics for whales. So these are major marine observing centers that give us a lot of information on how the system varies and how it changes. So this region is huge. You can see California easily fits on the shelf. 80% of the US coastline is in Alaska. Over 60% of the shell area is in Alaska. And this is the area that we're trying to measure. It's extremely rich. It provides 50% of the US catch of fish and shellfish by weight. It also supports subsistence harvest for about 60,000 people along the coast, and supports many endangered species, etc. Okay, so what drives this system and what controls this system? It's sea ice. Shown here is a particularly nice satellite image of sea ice. Ice forms on the Bering Sea shelf. First, the Chukchi freezes because it has to be cold. Then cold winds out of the north blow across the shelf and cool it. You begin to form ice mainly in the polynyas, which are next to land, and the water is opened up in those areas. It's very cold, it freezes, and the ice is pushed further south. You can see a number of polynyas. They're the slightly darker colors there. This was a very windy time and opened up a lot of open water that then froze. You also can see the flows of ice, the kind of larger islands in it, in the kind of rocky, broken up area. And the leading edge of the ice moves south and it cools the water. It melts and cools the water system. This ice is not flat. This is a plot in the lower left of the ice keel depth. The black line is the average depth, and you think, not much. Yeah, it's a meter, maybe 2 meters deep on average, thick on average. But if you look at the short term, the data every minute, you can see that there's huge variability. This is maximum keel depth. You can see in mid-March, there was a keel that went by that was over 20 meters deep. This is a very dynamic place. It's very uneven in the bottom, and ice is, this is what kind of controls this system. So a little bit more about ice. Typically in the Bering Sea, ice can arrive as early as October and remain into June. But typically it's more December through May. Shown in the upper left is a plot since the data go back to 1978. And it's what the percentage or how much ice, what area of the Bering Sea are you covering in ice? And you can see the blue line, which is 2012, which is the highest ice year that we have on record. Basically 1 million square kilometers of ice existed in the Bering Sea that year. The interesting part is 6 years later, 2018, we had the lowest ice extent on record. If you look at the two photos right beneath the satellite images, you can see these are basically, both of them are the beginning of April. You can see in 2012, ice was everywhere. You have the ice. There's also some clouds there. In 2019, I don't have an image for 18. You can see there was virtually no ice. There was no ice, not only, or very little ice in the Bering Sea, the southern Chukchi had no ice also, and that had never been seen before at this time. On the right is just a plot of how much of the shelf does the ice cover at maximum extent. At the top, maximum extent gives a date, so at maximum extent, you can see it's anywhere from late January into April. 2012 is by far the largest ice extent we have on record, and you can see it extended even out into the basin, onto the slope a little bit. Usually ice is located on the shelf. And then you can also see the solid red line, which is the maximum ice extent in 2018. So how does ice cool the system? As I said, ice advances over warmer water, it melts and cools the system. This is data from a mooring that we had deployed. And if we look at just the middle panel, the black line is percent ice covered in a 50 by 50 kilometer square centered on this mooring. And you can see the ice kind of arrives a little bit in early February. It increases rapidly. By February 6th, you're up at 60%, and then it continues to increase, reaching almost 100% in mid-March. The other data is the temperature at various depths. And you can see the color code at the bottom of 10, 18, 22 meters. And what happens is at the beginning, as ice arrived, the winds have been very strong, the system is well mixed, and temperatures are uniform. Ice arrives, it begins to melt. The bottom panel shows you begin to see the decreasing in salinity. The upper part of the column, water column, about the upper 30 meters or so, cools rapidly. And as the ice melts, The deeper part cools much more slowly. And it takes about 2 to 3 weeks to cool the whole water column. This water column at this location, it was about 74 meters. It took 1 meter of ice to melt to cool the water temperature, or the whole water column. And so this is how it works. It's not an instantaneous cooling. And this mechanism of how it cools works to about a depth of about 100 to 120 meters. The ice doesn't last long enough at deeper depths to cool the whole water column. But so this is how the ice cools the system. It takes a little bit of time. So let's go back to 2018. The red line at the bottom is the 10, 11 year, actually 12-year average temperatures at that location, at that mooring site. And they're the two mooring sites in the lower left-hand panel of things, the two red dots, the two northern. They have always had ice up to 2018. That was the first time there was no ice at those locations. Anyway, you can see what the temperatures were. Basically, it's below -1 historically at that time. 2018 was very different. You can see the temperatures were 4 degrees warmer than what the historically average were. And so this makes a big difference for the ecosystem and a variety of things. Both moorings showed a very similar pattern. So what else can ice do for this ecosystem besides controlling the temperature? Let's look at the base of the food web, the phytoplankton, algae, chlorophyll blooms that occur. In the upper right-hand corner is a schematic of how it works. You can see the ice. Underneath the ice, beginning usually sometime in February or March, you begin to get ice algae at the bottom. And the ice algae exists. It's a very good food source. Zooplankton like it because it's pretty concentrated and they just have to feed right underneath the ice. As the ice melts, that ice algae begins to fall to the bottom and it feeds the benthic communities. Ice regions typically have very strong benthic communities, and it's in large part due to this source of food that falls to the bottom. After the ice melts, sometimes you get a phytoplankton bloom. Sometimes you don't, but sometimes you do. And you usually get another bloom in the fall. In the lower left-hand corner is the timing of the chlorophyll presence. Once again, you look at the historical years. The dashed line is the 1-to-1 line. You see the ice melts, say ice retreat on day 100 or 150, and you see all the algae or the chlorophyll signal occurring just shortly after that ice melt, or after the ice completely retreats, except for 2018 and 2019. They're in a completely different world. You didn't see a bloom until maybe 40, 50, 60 days after ice retreat. This has strong indications about the food that goes to the benthic communities, because if there is no ice algae, you're not feeding that community. On the lower right is just the time series. And you can see how nice and sharp that time series is. This instrument is because of the 20-meter keel. Ice is at about 20 meters. And so what you're seeing is the ice algae falling below from the melting ice down. But here, what you're seeing in 18 and 19, what you're seeing is a phytoplankton bloom. So there's many ways that temperature can affect these ecosystems, and HABs is one of them, hazardous algal blooms. The lower left-hand map is from Don Anderson, and it's actually what concentration of cysts Not necessarily blooms, but the possibility of blooms are there. Some of the highest concentrations ever observed have been observed in this region in the CHUKCHI Sea, which is this red dot there. Very high concentrations of cysts. And as the system warms, it has now reached a point where widespread toxic blooms could become more common, and they will threaten the marine wildlife and the people who live there. There were sightings of walrus that had been poison toxic, and you could see them bending their back, and just, damaging their nervous system. So it's been observed. Historically, this has never been observed because the suspicion is the water was too cold for there to be toxic bloom. There's a variety of programs now looking at HABs up there. One of them is eco-HABs. And the main reason I'm showing this is a hard image to look at, but what it shows is how many groups and partnerships you need to make observations. Observations are so limited here that virtually every ship that goes north makes observations for other groups, simply because ship time is really difficult to come up with. So let's take a step back and look at what temperature actually does for this system. And the system we need to look at, or the idea we need to look at, is a thing called the cold pool. And shown in this panel on the left is the vertical temperature from January to December at M8, which is the northern mooring. The top is ice. And what you see is the water column is fairly well mixed. By February, it's very cold, minus 1.6 or 7. Ice hits a maximum in April and begins to decline, and the surface begins to warm. But the bottom 40 to 50 meters of the water column do not warm. And that's called the cold pool. It remains typically below 2 degrees. Sometimes it remains below 0. And that cold pool plays a real important role in what happens in this ecosystem. Just a quick look of the cold pool. On the left is the ice extent that we looked at before, and you can see the biggest cold pool that we have on record is 2012, which was also the most extensive ice. 2018 has a very, very small cold pool. Why? Oh, okay, this is just another image here of about 20 years of the cold pool. You can see there's a lot of variability. It's the blue colors on the right, and you can see how 2012, but there are other years that were similar to 12, 2008, 7, 9, and then the lowest year was 18, 19 not far behind, and 2003 was also a very small cold pool. And the cold pool on the bottom looks like this. If you look across the shelf, you're seeing it. The coastal region has strong tides. It mixes top to bottom. If you go far enough off, beyond 100 meters, the currents are too fast, so you don't hang on to the cold pool. But right in the center, between depths of about water depth of 50 to 100 meters, this purple area exists, and that is what the cold pool looks like across the shelf. So why is it important? It provides 3 things to the Bering Sea shelf. One is it provides a corridor for Arctic species, Arctic cod, saffron cod, snow crab, all kinds of species that need and like and inhabit cold water. It also provides a refuge for some young fish who are not as sensitive to colder temperatures, particularly pollock. Adult pollock have a nasty habit of eating their young. So if the pollock young go into the cold pool, the adults don't really care for it. And so the third one is it does provide a barrier for many subarctic species because their preference for temperatures are above 1 or 2 degrees. And so they will avoid this water. And you can see that in this next plot. The upper left-hand corner shows the cold pool, and the purple, and that's the pink color. This is a cold pool defined as 0 degrees, but it's similar to the others. The purple is where they see the adult pollock. In 2010, extensive cold pool, all the pollock were offshore. And this is historically what we've seen for the last 30, 40 years that we've worked up there. 2017 was a warm year, not as warm as 18 or 19. Cold pool was small, and pollock began to appear on the northern Bering Sea shelf. The communities found it really surprising because they weren't used to using pollock as a subsistence food. And then you can see in both 18 and 19, the pollock spread everywhere. In 2018 and 19, pollock extended into the Chukchi Sea, and the Russians commercially harvested them. The Chukchi Sea is more productive on the Russian side than on the US side. And so the pollock went to the Russian side because there's more food and et cetera there. So this is a real shock to us, and it was a real surprise. We were not predicting this as early as 18 and 19, but we suspect this is the future of the Bering Sea, of the northern Bering Sea. Okay, so the opposite thing is Arctic species can't like cold water, and so things like snow crab used to occupy most of the Bering Sea shelf. They're a very lucrative product. I'm sure everyone's had snow crab. They're delicious to say the least, but their population has been declining in different warm things. This is an article that the Seattle Times just printed this last week, actually, and it talks about what's happened to the snow crab and the low numbers we have up there now. And the suspicion is this is temperature related and the warming of the system, although it might also be related to the other thing I mentioned earlier about less food in the benthic communities because of less ice algae. Okay, the next thing is whales. Whales don't care about temperature. I mean, at least the Arctic whales don't. They have a lot of blubber. They're quite happy being up in -1 degree. But, and this is bowheads here, bowheads don't do well in deep ice. If your ice is 30 centimeters, they can break through it. But if it's deeper than that, they can't. And so they have to leave the region. If you look at the top line of the southern Chukchi at the bottom, this is some work of Catherine Burchak's. The black lines are, she has passive acoustics. She listens for bowheads and other whales. They're very talkative, so you can hear when they're in the region. And so the black lines is how often you heard them in a day from the things. And so you can see sometimes, they're talking, 40%, 50%. Sometimes it's 100%. You hear them just about every hour. And, but what you see is look at the 2012, remember a huge ice shear. The bowheads came south, retreating from the ice to the north. They continued south into the northern Bering. They continued south from the northern Bering, and they went all the way into the southern Bering. As the ice retreated, they also moved north, and you can see they returned in the northern Bering, and then they returned, and they continue north, and they feed in the far north. And you can see each of these years, 12 is real clear, but the other years you see also a gap. The bright blue line is ice extent at that time. So you can see when there's ice there. In 2018, for the first time, bowheads overwintered in the Chukchi Sea. Fortunately, the instrument failed in the northern Bering, but we suspect you also saw overwintering there. Although you might have seen a migration, less of them, but it's unfortunate it did fail, so we don't have that data. But this is a big change for the communities who harvest whales and need them to feed on. So anyway, so the final thing is people. People also are, this is a critical region for them. Ice plays a critical role. Directly, for instance, it provides a highway in the winter for them to move. They travel on the ice to other villages, to harvest things, etc. Ice damps waves. And so that means when you have a sheet of ice, it's wonderful. It's flat, calm, no waves. You don't get seasick. For them, no waves means no erosion of the coastline. And at the moment, we're beginning to see coastline erosion because the ice is there for less of the season. Winter storms are intense, and you're getting waves along the coast, and you're getting erosion. In a non-direct way, ice advance and loss impacts the food they eat. When is the food available? You can see the bowheads moving through the system at a very different time than historical. You're seeing pollock and salmon and other species arrive in these waters that they haven't harvested before. So they're changing their lifestyles and how they have lived here. So this is just a schematic of sea ice and what we discussed here, what it influences. It also has huge influences on bird die-offs, the transport of heat, zooplankton and nutrients, which I didn't discuss. So thank you. And are there any questions?
Question, anybody? Sure. I could just go up. Great presentation. So does your shore ice kind of follow the same patterns and characteristics as open ocean sea ice?
So coastal ice is a little bit different. First of all, it often becomes land fast, i.e. The coast is so shallow that it freezes to the bottom and it doesn't move. So when I showed that original image, I said the ice was pushed south by the winds. That doesn't happen along the coast. The coast freezes first because the land gets cold faster than the water. And so you begin to get a halo or an edging of ice along the thing. And then the shallow parts just remain frozen and remain solid until the next spring when they thaw and float away.
Thank you.
You mentioned that there's changes like with ice melt and stratification. Are you also seeing changes in the circulation in the area? Or is it like kind of?
So you're echoing a little bit, but did you ask, do we see changes in the circulation of the currents?
Yes.
Okay, there has been over the last 2 decades an increase of transport through Bering Strait. The flow in Bering Strait is northward. It transports heat, salt, and all kinds of larval fish, nutrients, that type of thing. That has increased from a historical average of about 0.8 swerdrups, 10 to the 6 meters cubed per second, to about 1.2. So there's more heat going north, and this has an impact on the CHUKCHI's ice because the Bering is warmer than CHUKCHI, so it affects warmer water, which more melts ice more rapidly. So the CHUKCHI's ice duration has decreased between 1 to 2 days per year over the last 30 years. So you've had a substantial loss of ice in the Chukchi, and part of it is due to the warmth in the Bering Sea.
Thank you.
All right, thank you. Thank you. Phyllis, for your talk. Okay.